This is lecture 8.6, which is an extension of what we've already talked about in equilibrium. We're going to use something called KSP in this lecture, so let's go ahead and get started. So in this chapter, in this unit, you're going to be working from chapter 19, which I know is a skip ahead, but we need to look at what KSP is and how that relates. So please make sure that you've completed these learning targets in your notebook before you watch the rest of the video. When you're ready, you can restart the video. Okay, let's go. So I'm going to make the details of this short and sweet because you should have most of this information already in your learning targets. I want to spend most of our time here in this lecture going through a few examples with you and how it really works. But there are some big ideas that you have to make sure that you're good at and that you understand before you start using this equilibrium twist, the idea of KSP. So I want to make sure that you are comfortable with a few things first. So what we want to look at is that KSP stands for solubility product constant, and it's the equilibrium situation between a solid and the ions that it dissolves into when you put it in water. So the equation will always be written as your solid on the left and your aqueous ions on the right. And you have to make sure that you're putting in coefficients to match the subscripts on the ions in the compound, so we'll talk about that. The thing that this helps you with a lot is that usually we only talk about KSP for salts that we used to call insoluble and now we're going to call slightly soluble. And really what this means is that they barely dissolve. So anything that we use KSP for is pretty much on your insoluble list on your solubility rules. So the same things work with KC and KP. We're still going to use ice charts. We're still going to write the equilibrium expression the same way. We're not including the solid in the equilibrium expression. I will put it in the ice chart because we will talk about that, but you're not going to solve for values in the ice chart. And so the questions that we've already done with the equilibrium constant and the solid there are really important as examples for how to do this. One thing that's new is that by definition, molar solubility is the number of moles per liter that is the maximum amount dissolved in a solution. And so these, for KSP substances that we do KSP questions for, this will be a very small amount. But basically what we're saying is that this is in a solution, how many moles of that solid would dissolve in 1 liter. And so this is really important. And so this is kind of the definition. You have to remember that if something is a saturated solution, I put that down here, that it is at equilibrium, which means that the maximum amount that has dissolved is dissolved. And for every one more formula unit that might dissolve, the ions would have to go back together to make a new formula unit, so as in the solid. So kind of keep that in mind. And since you know saturated means at equilibrium, it means anything that's about a saturated solution is telling you about the E line of your ice chart. Okay. We can still use Q versus K as well. And so when you're doing this, you want to picture that we can solve for Q the same way that we would in KC or KP by substituting in the concentrations. It's always concentrations in this case, but by substituting in the concentrations of the ions after they're mixed, but before they do anything. So the key is that if you're solving for Q, you have to find the molarities after they're mixed. And to do that, this will always be Vm equals Vm, where this is its original concentration and the volume that they tell you you're using, and this would be the mixed concentration or the mixed volume. So this is going to be total V always. All right, so we'll use that together too. And it works the same way as Q before, Q and K before, where Q greater than K means too much product, so the reaction would have to go back to the left. And since your solid is on the left, this means a precipitate would form. And Q less than K would mean that you have not enough product, so it would have to go to the right. And since your ions in solution are on the right, that would mean no precipitate would form. So this kind of gives you an overview of pretty much everything that you should have encountered as you were going through the learning targets. And so now I'm going to just do a couple of examples with you to illustrate how this works. So the first thing that's important is that you need to be comfortable writing the equation, the chemical equation that goes with a solid dissolving into ions, and then write the KSP expression from that. So I'm going to do the first few for you, and then I'll let you stop the video, and you can come back and try them yourself, and then check them when you've done that. So let's do the first one together. So they want the ion product expression, so that's KSP, and in order to do that, I need the equation first. So I'm going to do calcium sulfate. This is great naming and formula writing review. Calcium is 2+, sulfate is 2-, so the formula is CaSO4, and I'm going to put solid there. And then it's going to be at equilibrium with the two ions that form it. In this case, that would be Ca2+ and SO4 2-. Technically, these are in solution, so I'm going to include the AQ here now, but you know, you can kind of be sloppy for your own work, but I would definitely mark the solid. If this is the AP exam, you should put the AQs. All right. So notice then that the KSP for this would be the writing the K for this. And so KSP, it's always this equation. It's always KSP matches a chemical equation that has the solid on the left and the ions in solution on the right. So KSP will be something over 1, because this is a solid, we're not including it. And that would be, in this case, calcium 2+ ions times the concentration of the sulfate ions over 1, which in most cases then means that we don't even write that. And this is what your KSP looks like, your KSP expression. Okay, do the same thing for chromium 3 carbonate. Chromium 3, Cr3+, carbonate is CO3 2-. So the compound that forms from that, using the process of making the charges 0, would be Cr2, CO3 3 times, and this is a solid at equilibrium with the chromium 3 ion and the carbonate ion. And this has to be a balanced equation, so I need 2 of the chromium 3s and 3 of the carbonates. So for this, KSP would equal chromium 3+ squared from the coefficient times carbonate, CO3 2-, cubed from the coefficient. Okay? And so this would be the KSP expression for chromium 3 carbonate. I'm going to let you go ahead and stop the video and try the next two. And I'll just put the answers up, and if you need help, then you can check it from there. Be careful with charges. Remember that magnesium is 2+ and hydroxide is 1-, and aluminum is 3+ and hydroxide is 1-. So stop the video and then restart it. Okay, so for magnesium hydroxide, I'm not going to write the equation now. I think you should be okay. KSP would equal the magnesium ion times the hydroxide ion squared, because the coefficient would be 2 OHs in the equation. And for aluminum hydroxide, KSP would be the aluminum 3+ ion times the hydroxide ion cubed. And that's because your solid would be AlOH 3 times. So your number of aluminum ions is 1, but you have 3 hydroxide ions. Okay, so you can kind of see that pattern. All right, let's talk about solubility. Remember that solubility is talking about the max amount dissolved, and we're talking about molar solubility, so it's going to be in the units of molarity. All right, and so we can use our ice charts and KSP to solve for this. So I'm going to go ahead and set this up just to show you. They're telling us calcium phosphate, and they want to know what is the molar solubility, and they give us KSP. So the first thing I'm going to do is write my ice chart. This is your best friend, so always write your ice chart. So write your equation. Solid calcium phosphate forms calcium 2+ ions and phosphate, PO4 3- ions. Balance the equation from the subscripts to the coefficients. So this would be 3 calcium and 2 phosphates. I'm going to make my ice chart. This is a solid, so I'm ignoring it. And when we're talking about dissolving, we're talking about putting the solid in water. So our initial concentrations are always 0 as long as you're dissolving this in water. We'll talk about that a little bit differently next time, okay? But dissolving in water means there are no ions present, calcium or phosphate present yet. Since I have zeros, this has to go to the right. So this will be plus 3x, and this will be plus 2x. And then this bottom line will be 3x and 2x, okay? If I want the molar solubility, here's something that you need to know theory-wise, and that would be, since it's the maximum amount dissolved, we're talking about the solid, And if the solid were in our ice chart, it would be minus because it's dissolving and its coefficient is always a 1, so it would be minus x. So when we're talking about the maximum amount dissolved, it means solve for x, okay? So we need to solve for x in order to talk about molar solubility. And since x would be in molarity when we solve for it, it will be molar solubility. So the way that we're going to do this now is write our KSP expression. KSP equals, from the equation, the concentration of calcium ions cubed times the concentration of phosphate ions squared. And now I'm going to substitute in my equilibrium line, which would be KSP, they told me 1.2 times 10 to the negative 29th, notice how small that is, equals the calcium ion, which is 3x squared, the whole thing, not just the x, and 2x, the whole thing squared. So this now equals 3x cubed from the coefficient, I think I said squared. So this equals 3 cubed, which is 3 times 3 is 9 times 3 is 27, x cubed, times 2 squared, so 2 times 2 is 4, x squared. Okay, so you have to make sure you square and cube the numbers as well as the x's. And then I multiply that out and I get 108 x to the 5th equals 1.2 times 10 to the negative 29th. Now it's pretty easy to solve for x. I'm going to divide both sides by 108 and I'm going to take the 5th root. You can do this in your calculator however you'd like, but I usually do whatever that answer is. I didn't solve for it. I literally just divided by it and then did this. But take the 5th root would be solve for that answer to that and raise it to the, in parentheses, 1 divided by 5. Okay, so when I did that, I found that x equals 6.4439, some more numbers, times 10 to the negative 7th. Since my KSP is my only given value, it has 2 significant figures. I'm going to have to make this 6.4 times 10 to the negative 2nd, and since this is, everything is in concentration, that will be molarity, and this is my molar solubility. Okay, something that if you're reading your book, instead of using x, they use s, and this is just a way to help you remember that molar solubility is x. So if you look at your book, it will say minus s and plus 3s and plus 2s, and this would say 2s and this would say 3s, etc. I don't care whether you use x's or s's, but just be aware that often to help remember that the solubility is the x, people will substitute the s for the x in KSP questions. Okay, so let's do another one. This is going to go the other way. In this one, we're going to use solubility to solve for KSP. This is the other option. Either you're given solubility and you're solving for KSP, or you're given KSP and you're solving for solubility. So in this case, I'm going to do the same exact things as I did before. I'm going to write the equation. My solid is calcium fluoride, so CaF2 solid, at equilibrium with the calcium 2 plus ions and the F1 minus ions. There have to be 2 F1 minus ions. These would both be aqueous. And I'm going to write KSP, the expression, which would be the calcium ion times the fluoride ion squared. Really hard to see that, sorry. Okay, and now I'm going to see what I can do. I'm going to set up my ice chart. Remember, this is a solid, and these are zeros. If you want to change it to s's, now you can. Remember that this would be plus s, and this would be plus 2s. So this is 2s and s, or s and 2s in that order. And technically, if I want to solve for KSP, I need to know the value of s. So s has to be molar solubility, the most that will dissolve in the units of moles per liter. Okay, so notice that they tell me that they've pulverized this and shaken it all up, and they're basically telling you that in solution, 10 milliliters of solution, this many grams of CaF2 dissolved. So we need to convert that to moles per liter, but once we've done that, it's telling you the maximum amount dissolved. So it's telling you S. We just have to get it in the right units. So this is going to be 1.5 times 10 to the negative 4th grams of CaF2. In every, be careful because it's not in a liter, it's in 10 milliliters of that solution. So I'm going to convert milliliters to liters, and I'm going to convert grams to moles. So when I look up CaF2 on the periodic table, I find that its molar mass is 78.08 grams in 1 mole, and that gives me 1.9211 times 10 to the negative 4th molar. Okay, and remember that this is how much dissolved, so this is our molar solubility, so this equals S. That's the theory that you have to know. All right, so if this is our molar solubility and I want KSP, now I can, let's say they asked me for the concentration of the fluoride ion, I could just say 2S, but I need to substitute in for both of these. But rather than do that twice and then multiply, I just came in and did this. KSP equals S times 2S the quantity squared, which equals 4S cubed. And then I took this 1.921, this is not rounded to sig figs yet, and substituted it in for S and cubed it and multiplied it by 4. And I found that KSP equals 2.836, a bunch of numbers, but I have only 2 significant figures because of my 1.5 grams. So 2.8 times 10 to the negative 11th is the value of KSP. So there's your second option. The third thing I want to show you quickly is how to use Q and K to decide if a precipitate forms. So you need to make sure that when you're doing this, what you put into your Q expression as the molarity is the molarity after they've been mixed but before they react. So you have to read the question really carefully and decide, are they giving you the concentration of that ion in solution, or are they giving you the concentration of that ion when it's by itself in its own in the mixture? Sorry, start over. Are they giving you the concentration of the ion in the mixture, or are they giving you the concentration of the ion in its own solution in its own bottle all by itself? If they're giving it to you already in the mixture, you don't have to do VM. But most of the time, they're going to give it to you as in you have this many milliliters of this solution and this many milliliters of this solution, and you're going to pour them together, which means they're giving you the before you've mixed them molarities. All right, so you have to use VM. And in this case, I chose a question like that on purpose so that we could illustrate how to do it. So they're telling you that a great way to remove lead from wastewater or from drinking water, if you're in Flint, Michigan, would be to precipitate the lead out using maybe sodium sulfide. Okay, so it's hard to tell in this question, but you're looking for who is the insoluble solid, who is the salt that's insoluble. So we're going to mix together sodium sulfide and lead ions, and we know that sodium compounds are all soluble, so the sodium sulfide is soluble. It's not your thing that you need KSP for, all right? And then we are going to pour lead ions in there. So you have to picture that lead 2 sulfide, is the insoluble solid potentially that's going to form. This is important. And then you're going to write your expression or your equation. This is your solid, and it's going to form your 2 ions, and in this case, they're in a 1-to-1 ratio, all right? And then I'm going to go ahead and think about what this looks like in my ice chart. This is a solid, so I'm going to ignore it. And actually, I don't need to look at my ice chart because they're not asking me about initial versus equilibrium, so sorry, let me back up. I'm going to do my Q expression, which would be Pb2 plus, because they're asking me if a precipitate will form. You need to know Q versus K, right? Because if a precipitate forms, that means that the reaction would head this direction toward the solid. If the precipitate doesn't form, that means that the reaction would head this direction. That means no precipitate. So you have to use Q versus K to make your decision about what's happening there. All right, so Q would be this, just like K would be that, except that we don't know if we're at equilibrium or whether it's favoring the products or the reactants. So we're trying to figure that out. All right, so when I look at this, I need to know the concentrations after mixing before they react. All right, so I need to figure those out because they're telling me I have 2 different amounts in 2 different containers. Okay, so the concentration of the lead, Pb2 plus ion concentration, sorry, let me do this so it looks right, is going to be Vm equals Vm. And they don't even give me molarity of this. So this is actually a hard question. Usually you're given molarities of everything, but I need the initial molarity, so I have to solve for that first. Okay, so I'm going to do that off to the side. But they tell me we have 25 liters of this, and its initial molarity, let's solve for that over here, is the same as 0.015 grams of Pb2 plus per liter. But that's not in moles per liter, so I have to convert grams, to moles. And for Pb2 plus, the ion has the same mass, so this would be 1 mole is 207.2 grams, which gives me a molarity before I mix them of 7.2 times 10 to the negative fifth. All right, so that's going in here as my initial molarity. And my final volume, this is going to be final volume, I have to read the question. I have 25 liters of one and a half a liter of another. So add those two together and you get 25.5 liters times the molarity after they're mixed. All right. So I multiply and divide and I get the molarity of the Pb2 plus after mixing equals let's see, 7.05 times 10 to the negative fifth. So I rounded that to 7.1 times 10 to the negative fifth molar. Notice that the solution is mostly this lead solution anyway. It's 25 liters of it. So that's kind of why it's so close to that molarity of before. We need to do the same thing for the molarity of the sulfide ion after mixing, right? But before they react. So I'm going to do the same thing, VM. And this one's a little easier because they gave me the molarity of the sodium sulfide when it was in its half liter. So I have a half a liter of 0.10 molar sodium sulfide. Notice there's one sulfide in sodium sulfide. So this means that the molarity of the sulfide and the sodium sulfide are the same. You kind of have to be careful with that. Equals my new volume again, the same new volume I used before, the 25 liters plus the half a liter. And now I'm looking for the new molarity. You'll get really good at this. We do this a lot, okay? So now the new molarity of the sulfide after mixing is 0.00196, so I made it 0.0020 molar. Now my two values after mixing can go into Q, okay? So now I'm going to say Q equals, we're going to substitute in the lead, which was 7.1 times 10 to the negative fifth, and the sulfide, which was 0.0020 molar. And a lot of times I won't round here, but I took this from your textbook and they rounded, so just know that. Usually I'll leave numbers bigger there unless they've asked me for that concentration. So Q equals 1.42, 1.4 times 10 to the negative seventh. And now I need to compare it to K. But notice the question didn't give me K. I think they were trying to avoid giving away who the insoluble solid was. And so because this was from your textbook, you would have looked up K, KSP, from the back of the book. So I had to look it up. And KSP for this, when I looked it up, of lead to sulfide, was 3 times 10 to the negative 25th, really small, right? So, so now I know Q is this, and K is 3 times 10 to the negative 25th. Q is definitely larger than K, which means that I have too many products, which means my reactant's got to go left. And when I look at my equation, if my reaction comes left, it's going to form the solid. So my answer is yes, it's a precipitate, and that would be because Q is greater than K. So to return to equilibrium, or to form equilibrium, or to reach equilibrium, we had too many ions in the containers that we poured together, and it can't be at equilibrium like that. So to reach equilibrium, it must form reactants. Overall, the net changes toward the reactants, and that would be a precipitate. Okay, so there you go. So this is what we're going to work on when I see you again, and come ready with questions so that you can start to practice and we can kind of see how it goes.